Join now. Okay, and I want to share the camera. All right. Cool. Callie, can you hear me and see the camera? You can just type it in the chat. Yes? Okay, cool. Awesome. Perfecto. That's so much convenient. All right. Cool. All right. Go. Okay, cool. And I can see everything. Dope. Awesome. Cool. All right. So again, we're going to be doing this. The camera is super blurry today. Oh, I don't know what that's about. Yeah, that's what I want. Okay. Anyways. Ooh. All right. How are we doing today, everyone? Thumbs up, thumbs down, somewhere in between. I think it's going to be a lot of in-betweens today. It's cold and gloomy outside. It stinks. I'm also super tired. It rained a decent bit last night, and because of that, several residents at UV had their ceilings start leaking, and I was the emergency on-call maintenance guy last night. So I kept getting woken up in the middle of the night to go put buckets under ceiling fans, which stank. So I got like 3 hours of sleep last night. So if I am saying just a bunch of absolute horseradish today, let me know, and I'll try to stay on top of that. Cool. All right. Any questions, comments, concerns, cries of outrage about anything before we do some review? Did anyone pick out any specific problems that they wanted worked primarily, or should I just go from the top to bottom? Top to bottom. Everyone in agreement with that? Okay. All right. Cool. So the very beginning of this really just talks about all the important like formulas and stuff, right? So we've got like chapter 1 really is just talking about linear functions. So remembering y equals mx plus b. And another one that I'll put on here that I think will just serve as relevance, though you may not need it for the exam. I haven't written the exam yet, so. But remembering slope equals change in y over change in x, which is y2 minus y1 over x2 minus x1. So that is an important one. My phone won't turn, that's fine. That just tells you the slope between 2 points, right? Remember y equals mx plus b, that's slope times your input variable plus your y-intercept. That's just how you describe linear functions. Cool. And then the rest of what we're really talking about is conditional probability, Bayes' theorem, and then binomial probability. So when you talked about like the Bernoulli distribution and stuff like that. So conditional probability was that given, right? If I ask you the probability given something has already happened, I'm restricting all of my event space down to the subspace where that event has happened. Our typical example is car crashes given it's rained. So I take all the car crashes, that includes rained and not rained, and I restrict it down to the event where it has rained. right? So that's the probability that we're talking about there. Cool, cool, cool. All right. Product rules says that the intersection specifically of independent events, or the product rule is the intersection of events is given by the probability of the restricted space times the probability of the first given the second. If they're independent events, if A and B are independent, then the probability of A intersect B is probability of A times probability of B, right? Oh, and it says it right here. So I wrote that out for no reason. So if they're independent events, if the first doesn't affect the second in any way, then I can just multiply them together. For instance, like pulling balls out of a bag, those are mathematically independent events. So I just multiply probabilities through and go from there. If it's with replacement, at least. Like what's the probability that the first is red and the second is green? You're just multiplying probabilities through. If with replacement. If you don't have replacement, then it is conditional, and that's the first example that we'll do. Cool. There's the criterion for independent events. It should be that if they're independent, then restricting the first event to the second event doesn't change the outcome, right? So probability of E given F is just the probability of E. That means they're independent. Likewise, probability of F given E is just the probability of E. Cool. Realistically, we need both of those conditions to hold, but almost all the examples you'll see, if just the first one holds, they're independent. So a question you may see on the exam is, I give you some set of probabilities. I ask you to prove that the events are independent. For instance, if the events are, I pull someone out of the class with brown hair, I pull someone out of the class with blue eyes, I give you all the probabilities of those happening. You have to show that those are then mathematically independent events. Cool, cool. And we did a couple of examples of those in class. If you don't have all the lecture notes that would cover this exam, either ask your classmates or ask me, and you can snap some pictures of them. Cool. All right. Bayes' theorem talks about multiple events happening at the same time. Like I have different sort of events that could happen. And so if I want to talk about the probability that one of the events happens given some specific event, then this is the probability of the intersection of that specific event with this space over the probability of the space, where this probability of the space is just given by summing up the probability of all the individual things together. Cool, cool. We'll look at some examples of that to see what that really means. But again, this is something that we did in class. And then binomial probability formula. This was saying, like, if we're doing a Bernoulli trial, right? Remember that that's two outcomes, pass or fail, right? For example, flipping coins until you get a head, like you either get a head or you don't. That's a pass-fail type system. Then like you can find the probability of a certain amount of outcomes happening by using this. So for example, if I'm flipping a coin 10 times and I want to see what is the probability that I get exactly 3 heads, it'd be something like this. It would be 10 choose 3, and then the probability that I get it, 0.5 to the third, times the probability I don't get it, 0.5 to the 7th, right? Something like that would be an example of a Bernoulli trial where I use the binomial distribution to figure out the probability of exactly some number of events being the outcome. And again, we'll probably see some examples of that. Cool, cool. So these are the important ones to remember. If you have questions about like how to remember them or anything, I can try to give you some ideas of how to remember them. But yeah. And we got some practice problems. So I've just got a whole bunch of scratch paper, and I will like show the problem and then work it out on some scratch paper. All right. So the first one says, suppose an urn contains 8 red balls, 5 yellow balls, and 7 green balls. One is chosen at random, not replaced, and then the other is chosen, and then it gives us some things to figure out. What is the first thing I should do before I really do any of the probability here? What is a good number that I should have going into it? Wyatt? Total number of balls. Is that what you're going to say, Charles? Good deal. So the total balls, 8 plus 5 plus 7, is 20 total. That's an important number to have. Now, I can go through and do the certain things that it asks. The first thing it says find or draw and completely label the probability tree for the scenario. So starting with my first ring, there are 3 possible outcomes, each with their own probabilities. I can have red that has a probability of 8 in 20. I can have yellow that has a probability 5 out of 20. And I can have green with a probability 7 out of 20. I don't replace the balls. So how many balls will be in my next selection sample? 19, right? I took one out of the sample. So each of these can have one of the 3 outcomes, right? And it says I choose one, don't replace it, choose another one. So I only have 2 chunks here, like I only have 2 sets of branches here. So I can have red, yellow, or green, red, yellow, or green, red, yellow, or green. And this is also how I get my sample space, right? What are the possibilities I could choose? I could choose green, 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 yellow, green, red, yellow, green, yellow, 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 red, red, green, red, yellow, red, red, right? That's my entire 9 options in the sample space. If I go through and show that the permutations give me 9, that's also correct, right? It's order is important, right? Because I don't replace them, so my permutations give me that. Cool. If I've already drawn a green, then the number goes from 7 to 6. So I've got 6 left out of the 19 total, right? There were 7. I took a green out. That's what the G here is. And I'm left with 6 of those out of the 19 total. Say I took a green first. There are still 5 yellow. So the number of yellow doesn't change. That's 5 out of 20. And then the number of red doesn't, or 5 out of 19, my bad. And then red doesn't change, so there's still 8 out of 19. So the only one that changed was the one that I drew, right? And that makes sense. If I draw a red one out, that doesn't change the number of greens. Or if I draw a green one out, it only changes the total number of greens. The number of red and yellow are still the same. I can do the same thing here. So I still have 7 green. My yellow has gone down from 5 to 4, and my red stays the same. These are all out of 19. And then here, my green stays the same, so that's 7. My yellow stays the same, so that's 5. My red goes down 1, so that's 7. And then out of 19, out of 19, and out of 19. And it should be the case that all 3 of these numbers on each little set of 3 branches still adds up to 19, right? 7 plus 5 plus 7 is 19. 8 plus 4 plus 7 is 19. 8 plus 5 plus 6 is 19. So everything still adds up to 19, just like here, everything added up to 20. Cool, cool. Now, it asks for a couple questions. First, it says, find the probability that both are yellow. This, since I've drawn this in such a way that the probabilities are conditional, I can just multiply through now, right? They're not independent events, but the way that I've labeled my tree is the appropriate way such that I can just multiply straight across. So for example, yellow and yellow, which is part B here, I have my first yellow, 5 over 20, and then I go to my next yellow. On the yellow branch, the second yellow is 4 out of 19. Cool. And this is, what does this come? 1 out of 19? Because I get a 20 up top, 20 on the bottom, and then I'm left with a 19 down there. Cool, cool. So again, I didn't really do anything crazy here. I just labeled my tree in a good way so that any first and second choice I'm given, I can tell you the probability by just multiplying straight across. That's the benefit of doing like decision trees right here, probability trees, is that even if it's not independent events, these aren't independent because I'm not replacing the balls, I can still multiply straight across. If they were independent events, the labels on the second set of branches would all be different. Everything would be the exact same as before. So this would be 8 out of 20, 5 out of 20, 7 out of 20, so on and so forth, right? So for example, if these were independent, right? If I put the yellow back and then drew another one, it'd be 5 out of 20 times 5 out of 20, 25 out of 400, which simplifies to 1 and 8. So, cool. I think. Maybe not. 25 out of 200. 25 out of 400. Yeah, that sounds about 1 and 8. Cool. All right. Then C says find the probability that the first is red and the second is green. So red and then green. I go to my red branch. That's 8 out of 20. And then on that, I multiply by the green chunk. That's 7 out of 19. This is 56 out of 380, which simplifies to something. It says here simplifies to 14 out of 95. Does that make sense? Yeah, this 8 over 20 simplifies to divide both of them by 4, 2 out of 5. That's 14 over 95. Yeah, so that works out. Cool, cool. Any questions so far? Yes. Multiply this. This is 5 times 4 is 20. So 20 over 20 times 19. The 20 over 20 cancels. I'm left with just 1 over 19. So this just simplifies. Like what I mean here is, and let me do this. Let me just do this in the back of this. 5 times 4 over 20 times 19. That's 20 over 20 times 19, right? And then the 20s cancel. I'm left with 1 over 19. Does that make sense? Cool, cool. Any other questions? All right. Next one says, find the probability the second is red, given that the first is green. So red given green. So I'm given the green first. Red second, green first, maybe. Those aren't like squared or to the first power or anything. That's just how I'm denoting red first and green second. So I can either write this as the probability of red intersect green over probability of green, or I can just look at my tree. I go to the green branch and see what the probability of red is here. We'll see that those come out to the same thing. So I should be looking for 8 out of 19, right? Given green has been selected first, red then has a probability of 8 out of 19. Or I can just go through and do everything. So probability of red intersect green is probability of green times red. So green first, 7 over 20, and then times the green there, or the red there, I mean, that's 8 out of 19, right? So red intersect green. Oh, sorry. Thank you. Red intersect green, right? Green is first. So I go down the green branch, which had probability 17 out or 7 out of 20. And then I go to the red probability, which is 8 out of 19. And then I divide this just all by the probability of green, which is 7 out of 20. The 7 out of 20 and the 7 out of 20 cancel. And I'm left with just 8 out of 19, which is what I was looking for, right? If I restrict myself to green first, then 8 out of 19 is the probability of red following that. Cool, cool. So either I could use the formula or I can just look at my tree. Again, a very beneficial thing for drawing trees, especially in situations like this. All right. Next practice problem says, okay, we've done this one, this one, this one. Probability the first is red, given that the second is green. So this one's a little different. I've got all of the different green as the second option, and I have to refer to the first one, the red first. So this is going to be where we use this Bayes theorem right here, where I have to talk about all the conditional probabilities of the individual chunks and then refer backwards, right? So let me just turn this around so I can write close to here. So I'm just going to copy down my Bayes formula real quick. U1 given E, probability of U1 intersect E, and then all over these conditions. U1 plus so on and so forth. So we're looking specifically here for the probability that red is first, given green is second. So this is going to be the probability of their intersection, red first intersect green second, over the probability that green is second. And the probability that green is second is the sum of the individual chunks. So this first top I'm going to keep the same. Red first intersect green second, over, I have the different chunks that I need to work out. So let me go to another piece of paper. I'm going to write this down. Probability red first given green second is probability of red first intersect green second over probability of green second. This is probability of red first intersect green second over probability of red first intersect green second plus probability of yellow first intersect green second plus probability of green first intersect green second. So it's the way that I get red first over all of the ways that I get green second, right? And then I can further write out what these are. So probability of red first intersect green second. Probability of red first and green second is the probability of red first given green is second times the probability that red was first. Right? This is what we ended up writing out here. Plus probability that probability that yellow was first given green is second times the probability that yellow is first plus probability that green is first given green is second times looks a little complicated, but our tree helps us out. Right, we had our tree here, so that gives us all of our information that we need. I only wrote out the second line just to show you that it is Bayes' formula, but this line right here is the one I want to use. So probability of red first and green second. I just go here, probability of red first, 8 out of 20, times probability of green second, that's 7 out of 19 with red first. And then all these probabilities on the bottom. And let me zoom out a little bit, actually. So this red first and green second is the same thing as right here, 8 out of 20 times 7 out of 19, plus the yellow first and the green second. Yellow first is 5 out of 20. And then green second there is 7 out of 19. And then the probability that green is first and green is second. So probability that green is first, 7 out of 20. And then green is second is 6 out of 19. Cool. So that would be my total probability that I want to compute there. And then I could go through and compute this. One thing that I can do is I can factor out a 7 out of 19 on the bottom, which will be really convenient. It may not look like it because not everything is multiplied by 7 out of 19, right? This one doesn't have a 7 out of 19, but I can switch the numerators here. So this chunk is the same thing as 6 out of 20 times 7 out of 19. So I can factor out a 7 out of 19. So the top is the same. And then I'm factoring out my 7 out of 19 from all of these. I'm left with 8 out of 20, 5 out of 20, and 6 out of 20. Cool. And then these cancel. I'm left with 8 out of 20 divided by 6 out of 20. Is that out of 20? 8 out of 20, 7 out of 19. 5 out of 20, 7 out of 19. 7 out of 26 out of 19. And then I can factor out my 7 out of 19 and 7 out of 19. Right, that leaves me 8 out of 20. This leaves me 5 out of 20. And this leaves me, 6 out of 20. Oh, why did I just do over 6 out of 20? My bad. I completely just didn't write out the stuff on the bottom. 8 plus 5 plus 6 is 19. And then this is out of 20. So 8 out of 20 divided by 19 out of 20 is 8 out of 19. Cool.
Can you just like recompute it out like all together, like on a calculator or no?
Yeah, you could. I just didn't feel like getting my calculator out. Yeah, you can 100% just put this in a calculator. Just be very careful, and that's another reason why I didn't want to use my calculator. Be very careful since we're doing fractions and division and everything. If you don't type it exactly perfectly with all the parentheses and everything, it'll mistake like an addition or a division or somewhere, and then you'll get the wrong number. So, but yes, 100%, I would suggest using a calculator. Just be very careful with the final result there.
Yeah, because it's like a decimal.
If you do it with the calculator, like you could get the decimal for all of these, and then yeah, it's super simple.
You wouldn't care if it was a decimal?
No, because when I write my answer key, I write every answer as a fraction and the corresponding decimal out to like 3 decimal places. So as long as I see either one of those, I'm cool.
Okay.
So again, because this is a kind of complicated problem here, I just want to highlight what we did. The question was the probability that red is first given green is second. This is the probability that red is first to intersect green is second, which is just multiplying through the branches of my tree, over the probability that green is second. The probability that green is second is all of the different ways I can get green is second. So looking at my tree, that's my 8 out of 20 times my 7 out of 19, my 5 out of 20 times my 7 out of 19, and my 7 out of 20 times my 6 out of 19, right? So I'm adding up all the ways that I can get green second, which makes sense. Remember that the given, if I say blank given blank, and I like to harp on this a lot, that's restricting it to the second option. So I'm restricting it to the cases where green is second. And so I have the probability that green is second. I have 3 different ways I can get that. So I add up all of those different probabilities, and then that's the denominator. That's my restricted space that I want to talk about there. Cool. So it's kind of explaining what Bayes' formula is doing, because Bayes' formula, in my opinion, looks god-awful. Like this is really complicated, in my opinion. It's a lot simpler to just think about, okay, this is just a given problem, and the denominator here is all the probabilities that the second thing can happen. The probability that the second things can happen is like the first branch times the second branch for the first option, first branch, second branch for the second option, and so on and so forth. So if there were, 8 colors in here, it'd be all the ways that I could get the first colors and then multiplied by the probabilities of green on the second part of those branches. Cool. This is a problem, one of those problems that I'd suggest maybe make up your own version of the example and then go through and do it again. Maybe I could suggest I have 4 red, 2 orange. I'll put orange here. 3 yellow, 4 green, 1 blue, BL. And I ask you, what is the probability of green first given red is second? Right, so I want to draw out my tree, red, orange, yellow, green, blue, They all get their own probabilities, and then each of these split off to their own red, orange, yellow, green, blue, 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 red, orange, yellow, green, blue. So all of the different, there's 25 total options here. So I'd have 25 different options. And so my top would be probability of green first intersect red second over probability of green first intersect red second plus probability of so green and then red first intersect red second plus probability of orange first intersect red second plus so on and so forth. So just all the ways that I can have red second added up on the bottom, and then the one that I'm wanting specifically on the top. So this would be a not too difficult example you could go through and work out yourself. Cool. If you're interested in the solution to this one, let me know, and I can do that. All right. Cool. So we did that one. All right. Now on to problem 2. So suppose a family has 3 children. What is the probability the family has exactly 2 boys, given the middle child is a boy? So what do I need to do? I need to write out a sample space. So I can have, if my boy is my first child, so this is the first child. So I can have, there's only 2 branches, boy or girl. I can have boy or girl for the first child. The second child, which is the middle child, can be boy, and then it could be a boy, or it could be a girl, right? So this is boy first, boy second, boy first, girl second. This could be girl first, boy second, or girl first, girl second. And then the third child can be a boy or a girl. So I can do that for both these branches. Boy, girl, boy, boy, girl, girl. And then same thing over here. Girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Cool. Now the question is, what is the probability that the family has exactly 2 boys, given that the middle child is a boy? So I want to highlight all the options where the middle child is a boy. This one has a middle child as a boy. This one, this one, this one. All right, so there's 4 ways that the middle child can be a boy. That makes sense. If there's 8 total options, half of them have the middle child as a boy, half of them don't. We all good with that one? Good with that statement? Cool. And then of these, so 4 have middle boy. So I guess I could say probability that boy is second is equal to 4 out of 8, which is 1/2. And then it says, let me skip this up. Then it says, what is the probability to have exactly 2 boys, given that the middle child is a boy? So probability of 2 boys, given the middle child is a boy, is the probability of the intersection of these events, probability of 2 boys and boy is the second child, over the probability that the second child was a boy. This is kind of confusing notation, so I apologize for that. This is saying probability of exactly 2 boys, given a boy was the second child. You could write this out explicitly in words. That would probably be a little bit better, but I'll just keep it as this for now. So the probability that both the second child is a boy and there's exactly 2 boys is there's 4 options here. So it's going to be something out of 4. Of those, 1, 2 have exactly 2 boys. So there's 2 ways out of 4 that the middle child, or that there are exactly 2 boys and the middle child is a boy. Cool. Oh, this isn't 2 out of 4. This is 2 out of 8. There's 2 ways out of the 8 total options. Then the probability that the second child is a boy, this is 1/2, is 4 out of 8. Right? So again, the probability that it's both 2 boys and the middle child is a boy, we saw that there were, and I'll start them, this one and this one. Those are the 2 options out of all 8 total options where it's the case that it's both the middle child is a boy and there are exactly 2 boys. And the probability that their middle child was a boy, we saw was 4 out of 8, or 1/2. It was all the circled options. So then I just compute this out. This is 2 out of 4, which is 1/2. Cool. So given that a family had a middle child that is a boy, the odds are 1/2 that they have exactly 2 boys, which makes sense. They can either have boy, 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 girl, girl, boy, girl, girl, boy, boy, so on and so forth. So 2 of those options have a boy in the middle, and then the others don't. I can kind of write that out too. If I fix the boy to be in the middle, there's 4 total ways that I can do that. Either I can have a boy first or a girl first. Boy first can have a boy or a girl here, and then a girl or a boy here. So these are the 4 options where a boy is in the middle. Of these 2 have exactly 2 boys. So given this is the subspace we're working with, half of them have exactly 2 boys. That's what this question is asking for. But I can also just go through and compute everything out mathematically. And I can assign probabilities of these: half, 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 half. Everything has probabilities 1/2. And so I just keep multiplying through. Each of these outcomes is equally likely. If I multiply through each of them, you'll see is probability 1/8, which makes sense. And then I can go through and I can just mathematically do this. Probability that a boy is, or probability of exactly 2 boys, and probability of boy being second, I could add those things together. Cool. All right. Problem C, 3 says 3 cards are drawn at random without replacement from a regular deck of 52 cards. What is the probability the first is a heart, the second is red, and the third is black? So let me write that out. Probability that, what is it? First is heart. And then second equals red. And then the third is black. That's what we're looking for here. Cool. So if I take one out, the probability that the first one is a heart is 1 out of 4, which is the same thing as 13 out of 52, right? There are 4 suits in a deck. I'm taking one of those suits. I'm choosing from one of those suits. So there's a 1 in 4 chance the card I get is of that suit. Then if the first is a heart, I've removed one of the red cards. So then if this happened first, then the next one, how many red cards are there typically? There's 26, but I took one of them out when I took a red card out. And then because I took a card out, I now have 51 cards left over. So just to recap, I had 13 hearts to begin with. The hearts are red cards, so drawing a heart means I take out a red card, and the total card count went down too. And then the probability the third is black. I haven't touched any of the black cards yet, so there's still 26 of those. but my total number of cards has also gone down one more again. So out of 50. So mentally just think about it. I have 52 cards. I pull a heart out. That removes not only a heart, but that's also a red card and just a card in general. So my card count as a whole goes from 52 to 51. My red count goes from 26 to 25. Then my black count has stayed the same, so there's still 26 of those. But now I've removed 2 cards, so there's only 50 options left. Then I can multiply these out. 13 times 25 times 26 over 52 times 51 times 50. Let's see, this is 1/2. This is 1/2. So 13 over 4 times 51, 13 over 204. And I'm not doing that in my head, so I'll get a calculator out. 13 divided by 204 equals 0.064, because it says to round to 3 decimal places. So there's your 3rd decimal place. Cool. Which is the same thing as 6.4%. So if I'm randomly pulling cards from a deck, say for instance, you're playing the game Ride the Bus, if any of y'all have ever played that, it's a popular party game. You draw cards from a deck and you have to guess, like if it's a red or a black card, you guess the suit, you guess if it's higher or lower than a number. Something like that would be applicable to this. Say I'm drawing cards randomly and I'm trying to guess if the first one is a heart, the second one's red, and the third one's black. There's a 6.4% chance that I'm going to get it correct, and in turn, probably 100% chance that I'm going to get drunk as a consequence of that. It's a very unfortunate and unfair game mathematically. So that was fun. I'm encouraging this. Not actually. How many of y'all are over 21? Okay, so I am not encouraging you to play this game in any way whatsoever. Cool. All right. Now 4 says, I'll turn the paper around for this. I'm given the probability of A equals 0.4. I'm just going to write down the problem. Probability of A intersect B is 0.12. If A and B are independent, what is the probability of B given A? So if A and B are independent, probability of B given A is just the probability of B. Cool. And I know that if independent, probability of A intersect B is the probability of A times the probability of B. Cool. So I'm just looking for the probability of B. I get 0.12, since I'm given the probability of A intersect B, is equal to 0.3 times the probability of B. Cool. Divide by 0.3 on both sides. And I get that the probability of B is 0.4. Cool. And that is exactly what I was looking for, right? The condition of them being independent enforces this first thing and this second thing. It enforces that the probability of B given A is the same as the probability of B, and the probability of their intersection is the product of their probabilities. That's all the information that I needed to be able to solve for here. Cool. So this is a pretty short and sweet example that kind of highlights that given these 2 pieces of information, I'm able to figure out basically everything about this system mathematically. Any questions about this? I went through it kind of quickly. Would anyone like me to do this again? If you do that, it's A-okay. I see a couple word faces, so I'm going to do it again. So I'm given that the probability of A is 0.4. And the probability of A intersect B is 0.12. And A and B are independent. The probability, or A and B being independent events, tells me two things. It tells me that the probability of A given B is the same thing as the probability of A, or likewise, the probability of B given A is the probability of B, right? They don't change each other in any way. They're independent. And likewise, the probability of A intersect B is the probability of A times the probability of B. Cool, cool? Cool, cool. All right. That's information that you are expected to know. So be that as it may, important for you to remember that independent events determine these two things. Cool, cool. With this information, I can figure something out. I'm told to find probability of B given A equals what? Well, since I know they're independent, I know it's going to be the same as probability of B. Probability of B given A is the probability of B. What I also know is that the probability of A intersect B is the probability of A times the probability of B, and that's equal to 0.12. I also know what the probability of A is. They gave it to me. So 0.4 times the probability of B equals 0.12. Cool. So I just divide by 0.4. Divide by 0.4. I get the probability of B is equal to 0.3. And boy, howdy, wouldn't you know it, probability of B is exactly what I was looking for because the independent events enforced this condition right here. So that tells me that the probability of B given A is equal to 0.3. Cool, cool. All right. All right. We only have a couple of minutes left. Is there anything particular from the probability or from the linear equations that y'all want me to go over? And what I'll do is I'll go through and I will send y'all the solutions to all of these. And you can basically use this as a practice exam. When I write the exam, I'm gonna draw from this quite a bit. So be comfortable with this study guide, and I'll send out the solutions in just a little bit. Cool, cool. If you have any questions about anything in specific, text or email me. I'll walk you through the problem. And yeah, don't forget the exam is on Wednesday. Please be here. I'm going to be very, very harsh on not doing makeups for this exam unless you have a good reason. Yeah.
I forgot my notebook.
Yeah. There's quite a bit, so I'll just let you take pictures of it. Huh? No, I sent it in email. I just copied myself one. Yeah. No, you're good. Maybe a lab, so you don't have to worry about that. You can make it my office hours.
Okay.
But it's not much. I expect a lot of people to be gone on Friday, so I'm not too worried about it. Yeah, it's not going to be like an Excel linear regression, but it's going to be a couple of questions about like, I give you the scenario, write the linear equation for it, maybe find the break-even point for a financial example. Yes, you can make them up in my office hours. I have office hours. What's today, Monday? Tomorrow before 12:30, Thursday before 12:30. Just any time. Let me know what time you want to do. I can get here as early as you need.
Okay.
It is, is it in the back of the book? I don't know if it's in the back of the book, but I sent it out as an email.
Oh.
Guess I should have it.
Okay.